This is a video for AQA Further Pure Mathematics, Matrices section 4.1, where we're looking at the idea of row and column operations to find determinants of matrices. So I want to look at what happens when we manipulate a matrix in different ways and how that affects the value of the determinant. So if we've got a matrix M which is 2, 1, 3, 4, then obviously the determinant of that is 2 multiplied by 4 and then minus 1 multiplied by 3, so giving us a value of 5. The transpose of the matrix is where we write what were originally rows as columns. So we've now got the first column as being 2, 1 and the second column being 3, 4. If we look at the value of the matrix, then we can see that we still get here that it's equal to 2 multiplied by 4 and then minus 1 multiplied by 3. So we get that it's still equal to 5, so that the determinant of the transpose of a matrix is equal to the determinant of the matrix itself. This time we've swapped a row, or indeed it could be a column, and you can check for yourself that these are really equivalent. So here we've swapped the second row and the first row round. So now if we look at the determinant of this new matrix, we get 3 multiplied by 1 minus 2 multiplied by 4, which gives negative 5. And in general, it's true that if we interchange a row or column, then the matrix will have a determinant which is negative of the original determinant. If we add or subtract multiples of a row or column, so here this is a new matrix where we've added 2 lots of row 2 to row 1 to produce a new matrix. Here this is row 1 plus 2 times row 2 of the original matrix. If we calculate the determinant of P, then this is 8 multiplied by 4 minus 3 multiplied by 9, which is also equal to 5. And that's true in general, that adding or subtracting multiples of rows or columns to each other leaves the determinant unchanged. So we can see here that this determinant P was equal to the original determinant of M. Finally, I want to consider what happens when we multiply a row by a scalar. So here you can see that we've multiplied the row by 5, and then the determinant of R becomes 5 times the determinant of M. And again, a general result. Multiplying by a scalar produces a matrix which has got determinant equal to that scalar multiple of the original determinant. In summary then, we have the following results. Transposing a matrix leaves the determinant exactly the same. If we interchange a row or a column, then we get negative of the original determinant for our new determinant. Adding or subtracting rows or columns leaves again the determinant unchanged, and multiplying by a scalar multiplies the matrix by that scalar. Now, these are by no means proof that we've done here. These are just examples to hopefully convince you that these results are true. However, they can all be proved algebraically, quite straightforwardly, and you might like to research that idea for yourselves. So you need to be familiar with these results and be able to use them. Transposing the matrix leaves it determinant unchanged. Adding or subtracting a multiple of rows or columns to another row or column, again, does not affect the determinant. Interchanging rows or columns changes the sign of the determinant, and multiplying by a scalar multiplies the determinant by that scalar. So 4 results there that you need to be familiar with. Now these results can be very useful when we're trying to evaluate a determinant, particularly determinants of higher order matrices. So for example, if we've got a 3 by 3 matrix, if we can, by using row operations, arrange for elements in a row or column for that matter to be zeros, then evaluating this matrix is very, very straightforward, because here we can see that we would only have A multiplied by the determinant given by that little 2 by 2 part of the original matrix. In other words, it's equal to A multiplied by the determinant of Q, R, T and U. And that's very, very straightforward to evaluate. The other parts of the 3 by 3 determinant would be 0. So to show that in action, I've got a particular example, and here I want to consider this particular determinant. Now we could go through and take 4 multiplied by the determinant of -2, 3, 1, 4, etc. However, let's see what happens if we use some row operations. So for example, we could take row 1 and add to it 4 lots of row 2. And if you do that, we produce a new matrix which has got 0, 0 and 17, and then the other 2 rows are still the same. And now we've produced a matrix which has got zeros in the top row, and apart from the last element, which was 17. So therefore its determinant is very, very straightforward, because it will just be equal to 17 multiplied by the determinant of -1, -2, 2 and 1. So that's equal to 17 multiplied by -1 multiplied by 1 minus 2 multiplied by -2. And that's equal to 17 multiplied by 3, which is equal to 51. So in summary then, we used this particular row operation to create zeros in one of the rows. It could equally well have been row operations which produce zeros in a column. In this case, we end up with 2 zeros, so that the determinant is then particularly easy to calculate. And because we've used this particular row operation where we've added a multiple of a row to another row, then we know that the determinant is unchanged. It was then straightforward to calculate that new determinant as being 51. Well, that concludes this video on determining the values of determinants with row and column operations. We'll see how these similar ideas can then be used for factorizing 3 by 3 determinants.